So hello everyone. Today we will be discussing some problems on distribution function from the book Castle Budget. The first example we are showing is pertaining to geometric distribution, and the problem is defined as tossing for a head. So in this problem, we are tossing a coin, and we are waiting. Waiting to get first head. So we define here x as the number of trials required to obtain to get first head. So this is the way x is defined, and we are also given that probability of head is p and probability of tail is 1 minus p, and I am writing it as q. Now we will write the probability that x is equal to 1. What does it mean? It means that we are getting a head on the first trial, so it is the probability p. Now second case is probability that x is equal to 2. Means we are getting the head for the first time at second trial. So for the first trial we get a tail, and then we got a head. And similarly, probability of x is equal to 3 will be q into p, so it will be q square p. So if we want to write the generalization of this PMF, so we will be writing probability that x is equal to, say, k will be equal to p and q to the power k minus 1. Or we can write it as probability of x is equal to x to the power x to the power q to the power x minus 1. Now let's write the distribution function of this. So distribution function f of x at a point, say, k, is defined as summation of x taking from value 1 to k p q to the power x minus 1. So we can take p outside the summation for x is equal to 1 to k q to the power x minus 1. Now I am opening this series, so this series will give q to the power 0 plus q to the power 1 up to q to the power k minus 1. So this portion is p and 1 minus q to the power k upon 1 minus q. So we are given that 1 minus q is p. So this cancels out and we get the distribution function as 1 upon q to the power k. Or we can write it as 1 minus p to the power k. So this is the CDF of or distribution function of geometric distribution. The geometric distribution. For the sake of simplicity, what we are presuming here is that if we assume that probability p is equal to q is equal to half. So in that scenario, what will be the effects? At 1 will be 1 by 2. f of x at 2 will be 1 minus 1 upon 2 to the power 2, which is nothing but 3 by 4. And f of x at 3 will be 1 minus 1 upon 2 to the power 3, which will be 7 upon 8. And f of x at 4 will be 1 minus 1 upon 2 to the power 4, which will be 15 upon 16. And for fx at 5 will be 1 minus 1 upon 2 to the power 5, which will be 31 upon 32. So we see that fx is increasing from the value 1 by 2 to 3 by 4, 7 by 8, 15 by 16 and 31 by 2. So now we will plot the, first we will check the properties of distribution function. So f of x at minus infinity, so we are having the value of x is equal to 1 to infinity, so f of x at minus infinity is 0, f of x at plus infinity, so it is limit a x tends to infinity 1 minus q to the power x. Since q to the power q is lying between 0 and 1, so q to the power k will be 0. So we are getting f of x at infinity is 1. Also, it is worth noting that f of x at x plus epsilon will be equal to f of x for small epsilon. It implies that f of x is right continuous. Here we should note that this epsilon is small. It should not be, suppose you are taking f of x at 1 and epsilon is also 1, then it is not equal to f at 2. So it is actually f at 2, which is not equal to f at 1. So you cannot take epsilon to be large. So this case will not be allowed. So we are saying that fx is right continuous, and also we see that fx is increasing since it is getting the value at 1, 3 by 4, 7 by 8, 15 by 16 and 30 by 2. So this way we are establishing that fx is a non-decreasing function. So this way we have established that distribution function fx, which is defined as fx k at 1 minus 2 to the power k, is a distribution function. So if we try to plot this curve, so I am just plotting it on the so what kind of curve we will have, what kind of graph we will see that. So we are getting x is equal to 1, 2, 3, 4, 5 and 6 and so on. So we are given that f of x is 0 for the interval x less than 0, and that x is equal to 1, say we are saying it to be 1 by 2. So fx will jump to this place and will continue till 2, it will reach here, and then 2, at 2 it will be 3 by 4. And for x is equal to 3, it will be 7 by 8. And at x is equal to 4, it will be 15 by 16. And similarly, as we will keep on increasing, this interval between two consecutive numbers will keep on decreasing, and at, so this is 1, then at 1 this will take a curve like this, and it will be touching this line 1, x is equal to, that y is equal to 1 at x tends to infinity. So this way the CDF of geometry distribution is defined. Now we will take some more examples on the distribution function. You can note it down. So this is the way the geometric distribution is defined. And now we will take another example. Which is called logistic distribution. What happens in logistic distribution? In logistic distribution, fx is defined as one upon 1 plus e to the power minus x, for x belonging to. So we will check the properties of distribution function. So f of x at minus infinity is 1 upon 1 plus e to the power minus of minus infinity, so which is 0. Similarly, the value of f of x at plus infinity will be defined as 1 upon 1 plus e to the power minus infinity. So this is equal to 1. Now to establish that fx is a non-decreasing function, we take the derivative of fx, which is f dash x, which comes out to be minus 1 upon 1 plus e to the power minus x to the whole square, and e to the power minus x and minus 1. So this minus cancels out, and it comes out to be e to the power x over 1 plus e to the power minus x to the power, which is always greater than 0 for every x belonging to 1. So we established that fx is a non-decreasing function. Also, fxx is continuous. So it is also right continuous, because algebraic function of fx is right continuous. all the properties of distribution function are satisfied by f of xx is nothing but it is a case of logistic distribution. So we established that fx is a logistic distribution which is defined by this function is also a distribution function. In the next example, we will show a CDF with a CDF and which will be increasing at y is equal to 0, which is having a jump at y is equal to 0, and then thereafter we will also check whether that particular function is also a distribution function or not. You can note it down and then we will proceed further. This example is from the book Kessler and Burgess. It's called CDF with jumps. So we are given that let f of y is defined as 1 minus epsilon to the power 1 plus e to the power minus y for y less than 0 and epsilon plus 1 minus epsilon upon 1 plus e to the power minus 1 for y greater than 0. So we have to establish that so that fy is a distribution function and find the jump at y is equal to 0. So we are going to check whether this function is a distribution function or not, and then thereafter we will check the properties of distribution function and we will also compute the jump at y is equal to 0. So to establish that, first property is f of y at minus infinity. So once we see for y is less than 0, the distribution function is given as 1 minus epsilon upon 1 plus e to the power minus of minus infinity. So it is 1 minus epsilon upon 1 plus e to the power infinity, which is equal to 0. Now let's check the value of f of y at plus infinity. So at plus infinity we are given that we are given distribution function as this: limit y tends to infinity 1 minus epsilon upon 1 plus e to the power minus 1. So this is equal to 1 plus epsilon plus 1 minus epsilon upon 1 plus e to the power minus infinity. So this term is 0. So we got epsilon plus 1 minus epsilon, which is 1. So this way we have checked whether the value of fy at plus infinity and fy at minus infinity. Now to check whether the function is function is decreasing or non-decreasing, we will take for y less than 0, fy which is derivative of f dash y, which is, so it is 1 minus epsilon to the power 1 upon e to the power minus y to the power whole square and minus times and e to the power minus y into minus 1. So this minus cancels out and it is 1 minus epsilon upon 1 plus e to the power minus y whole square and multiplied by e to the power minus 1, which is always positive for y less than 0. Similarly, for y greater than 0, f of y will be 0, will be derivative of epsilon plus 1 minus epsilon upon 1 plus e to the power minus 1. The derivative of this will be 1 minus epsilon upon 1 plus e to the power minus y to the power whole square and minus times and e to the power minus y and minus 1. So this minus cancels out and it comes out to be 1 minus epsilon e to the power minus y upon 1 plus e to the power minus y to the whole square, which is also positive. So we established that fy is an increasing function for both y is greater than 0 and y is less than 0. So this way we have established that this function is non-decreasing, and also since it is an algebraic function, which is continuous everywhere, which is continuous, so f of x is also right continuous. So this way we have established that fx is a right continuous. As now we will compute the jump at probability of jump at 0 will be equal to probability of, here we have equality to probability of y, probability of 0 plus 0 minus probability of probability of y is equal to 0 minus probability of y at probability of 0 minus. So probability of at y is epsilon plus 1 minus epsilon upon 1 plus 1 minus probability of 1 minus epsilon upon 1 plus 0, 1 plus 1. So what we get? Epsilon plus 1 minus epsilon upon 2 minus 1 minus epsilon upon 2. So this 1 by 2 cancels out. So we get the jump epsilon plus 1 minus epsilon upon 2 minus 1 upon 2 plus epsilon upon 2. So this 1 by 2 is cancelled out. It is comes out again epsilon by 2 epsilon 2. So jump is equal to epsilon. So we observe that the jump at y is equal to 0 is epsilon. So there we find the jump of this distribution, this function at y is equal to 0. So this is the second example we have taken. Now we will take some more examples on the distribution function. You can note it down. Now next we will consider the identical distributions. So what are the properties of identical distribution? Identical distributions are those distributions which are having the same distribution for all the points for all the whole range of x. So we will be giving you a definition, and we will see how a contradiction can also happen. So we are now discussing identically distributed random variables. So the definition of identically distributed random variables says x and y will be are identically distributed if for any a belonging to a probability, the probability that x belonging to a is equal to probability of y belonging to a. So this is the property of two random variables x and y to be identically distributed. Now here we see that if x and y are identically distributed, then their moments are also the same, and similarly in the inference we will be dealing with the independently and identically distributed random variables. Now I just want to bring to your kind notice that if x and y are identically distributed, then it doesn't imply that both the random variables are the same. So this we will establish with the help of an example. If x and y are identically distributed, it does not imply that x and y are same. To establish this, we will take an example of tossing a coin thrice. Let a coin is being tossed thrice. So now we define x as the number of heads in tossing a coin dice, and y as the number of tails obtained in tossing a coin size. So for this, I will first write the whole sample space. So there will be 8 cases. So first case I am taking is tail, tail, and tail. So we can write the cases here. First case is tail, tail, and tail. Second case is first head, tail, and tail, and tail, head, and tail, and tail, tail, and head. Now I will take into 2 heads. So head, head, and tail, head, tail, and head, and tail, head, and head, and head. And last case will be all heads. So in this scenario, we will take the values, compute the values of x and y. So what will be the probability that x is equal to 0? So here the value of x is 0. Here the value of x is 1. Here also x has the value 1. Here also x is having the value 1. Here x is having the value 2. Here also 2. Here also 2. And here the x is having the value 3. Similarly for y is having the value 3 here. Y is having the value 2 here. Y is having the value 2 here. Y is having the value 2 here. Y is having a value of 1 here, 1 here, and 1 here, and 0 here. So now we will see that what is the probability of x is equal to 0. It is 1 by 8. And similarly, this is exactly the probability of y is equal to 0. So x is equal to 0 only in one case, and y is equal to 0 is in this case. Similarly, probability of x is equal to 1. X is equal to 1 is obtained for these 3 values. So it is 3 by 8. And this is also equal to probability of y is equal to 1, because we are getting the values of y is equal to 1 for these 3 cases. Similarly, probability of x is equal to 2 will be equal to, again, x is equal to 2, 3 by 8, which is exactly the probability of y is equal to 2. So y is equal to 2 is this case. And moreover, probability of x is equal to 3, we are having the probability 1 by 8, which is exactly the probability of y is equal to 3. So this way we have shown that all the points are having the different probabilities, but x and y are identically distributed. All the probabilities are the same. For x is equal to 0, y is equal to 0, x is equal to 1, and y is equal to 1, and so on. So we have established that x and y are having identical distribution, but they are not same, because one is the number of heads and the other one is the number of tails. So we will always have to keep this in mind, that if we are given the fact that two random variables are identically distributed, it doesn't necessarily imply that the random variables are the same. So you can note down this example, then we will proceed further. So in respect of identical distributed functions, two statements are identical. First is are identically distributed. If we are given this, then it implies that second statement is f of x at x is exactly equal to f of y at x for all x. So if we want to establish this, then we have already defined that x and y probability that x is belonging to A is equal to probability of y belonging to A. Now let us define A as the of this. Then what we will get? Probability that x is belonging to this interval minus infinity to plus x, which will be equal to probability of y belonging to minus infinity to x. So what is this? This is f of x at x, and f of this is f of y at x. So this way we have established that these two statements are equivalent. Now I will take another example from the book Kessler and Berger, where we will have to establish that a function which is defined as f of x as e to the power of e to the power minus x for x belonging to is a distribution function. So to prove this, we will check the properties of f of x at minus infinity, which will be equal to e to the power minus of e to the power minus of minus infinity. So it will become e to the power minus e to the power infinity, which is e to the power minus infinity, which is 1 upon e to the power infinity, which is 0. So this way we saw that f of x at minus infinity is 0. Now f of x at plus infinity. So we will see e to the power minus of e to the power minus of infinity. So e to the power minus infinity is e to the power 0, which is 1. So this way we have established that the basic properties of f of x at minus infinity plus infinity are established. Now to check the function is a non-decreasing function, we take fx. This is derivative of f of x, which will be e to the power minus of e to the power minus x, then derivative of minus of e to the power minus x, so e to the power minus of e to the power minus x multiplied by e to the power minus x and minus 1. So we saw that this minus and this minus will cancel out. So it will be e to the power minus of e to the power minus x in e to the power x, which will be always positive. So we establish that e to the power x fx is non-decreasing. So this way we have established this. The fx is, now we will check the continuity. Since exponential functions are continuous, so we can conclude that f of x is continuous everywhere. So it is also right continuous. So this way we have seen another example of distribution function. Now I will take some more examples for the distribution function. So in this example, we are given a combination of fx let f1 and f2 are distribution functions, and a and b are two positive constants such that a is greater than 0, b is greater than 0, and a plus b is 1. Then we have to show that f of x, which is defined as a times f1x plus b times f2x, is also a distribution function. So this is the problem statement. Now we will check the properties of distribution function for this particular function. So let x1 is greater than x2. Since fx is a distribution function, so f1 x1 will be less than equal to f1 of x2. Similarly, for f2, x1 will be less than equal to f2 and x2. Now we will multiply this inequality by a and this inequality by b, and we'll add both the inequalities. This is equation 1 and this is equation 2. So multiplying 1 by a plus inequality 2 by b, we see that a times f1 of x1 plus b times f2 at x1 will be less than equal to a times f1 of x2 plus b times f2 of x2. So what is this by the property of what is this? So this is capital Fx at x1, which is less than equal to f of x at x2. So we see that Fx is a non-decreasing function. Now, therefore, we check if f of x at plus infinity. So we are given that a plus f1 of plus infinity is and b times f2 of plus infinity. Since we are infinity, this will be a plus b is 1, here is 1. Now similarly, f of x at minus infinity, we are given a of f1 at minus infinity plus b times f2 of at minus infinity. Since these terms are also distribution functions, so the at minus infinity these terms will be 0. So it will be a into 0 plus b into 0, which is again a 0. Now to check the right continuity, we will check that f of x at x plus h, where limit s tends to 0. So a times the limit s tends to 0, f of x, f1 of x plus h plus b times the limit s tends to 0, f2 at x plus h. Since these two are also distribution functions, so these are also right continuous. So we get f of f1 at x plus b times f2 at x. So which is nothing but which is f of x at x. So we established that fx is right continuous. So this way we establish that a function f, which is defined as as a f1x plus b f2 is subject to the condition that a plus b are positive and a and b are sum of a and b is 0 is 1, then this function fx is also again a distribution function. So this way we have we will construct two more examples which will be a function of a distribution function, and those will again turn out to be a distribution function. So here I define let another example on distribution from here. Let fx is a distribution function and h is greater than 0, then the function, say g of x, which is over h limits x to x plus h into f of u into du, and hx, which is 1 upon 2h limit x minus h to x plus h f of u into du are also distribution functions. We have to establish this fact that f and g and h are also distribution functions. So to begin with, let us take first the gx. So for gx, we will simply define that. Suppose to establish that fx gx is non-decreasing function, we know that if x1 is less than equal to x2, then say for some u x1 plus u, this property will also be true for some u greater than 0, and similarly f of x1 plus u will be less than equal to f of x2 plus u. Okay, now I will integrate both the sides with respect to 0 to h f of x1 plus u into du, and similarly 1 upon h limit 0 to h f of x2 plus u into du. So why one should always keep in mind this u I am adding here just to integrate it over the limit 0 to h, and when I will put x1 plus u as v, then or x2 plus u, say u and w, then this will turn out to be limit 1 over 2, and we will get this by this substitution. We will get this kind of form. Okay, so we will get what we will get x to x plus h, and this fx plus u will reduce to f into v into dv, so which is less than equal to 1 over h. This will be x1, and this will be x2 to x2 plus h f of w into dw. So this is what this is f of, this is g at x1, and this is g at x2. So by this by adding this constant u and then integrating this u over the limits 0 to h and dividing by h, since h is greater than 0, so we brought the x1 plus u to the limits by adding x1 plus u, by substituting x1 plus u is equal to x1 plus u is equal to v, and we will get the range x1 to get the range in the form of x2 x plus h. So here this way we establish that gx is non-decreasing function. This problem is from the book Gupta Rajgupta. Now we have established one first property of Gx. Now we will establish the rest of the properties for of Gx. So for the establishing the property of Gx, we know that g of x is defined as 1 over h x2 x plus h into f of u into du. Now we know that this fu is an increasing function. So what we will do in the first instance, we will take this fu to upper limit, and then in the second instance we will take it to the lower limit. So what we will do here, so we will write g of x is equal to 1 over h. Now since this fu is attaining the highest value at x plus h, so we will be replacing fu, we will be substituting fu in place of fx plus h. So we will take f of x plus h outside the integration, and if you will integrate this x to x plus h into du, so we will get h, so this will be cancelled out, so we will get gx is less than equal to f of x plus h. So this we have established. Now we will replace this fg of x with the smaller value, because fx will be having the least value in this interval, so gx will become greater than 1 over h f of x, and this integration will be root x to x plus h into du, so this will be equal to fx. So what we get, we can see that now g of x is lying between two functions of f of x at x plus h and f of x. Now what we will take the limits of x at plus infinity and minus infinity. So if we take the limit x tends to plus infinity of f of x and limit gx, so we know that this function is 1, this is g at plus infinity, and this function is always 1. So we see that gx at plus infinity will be unity. So this is the way we took the limits. Now gx, since gx is lying between f of x plus h and f of x, now we are taking the limit x tends to minus infinity. So f of x and limit g of x tends to minus infinity and limit x tends to minus infinity f of x plus h. So we know that as limit this approaches to this will 1 and limit g at plus infinity, g at minus infinity, sorry, since x is approaching to minus infinity, so this is 0 and gx is lying between two zeros, so gx is also gx at minus infinity is 0. So we established three basic requirements. First is was the gx is an increasing function. Second property was that gx is at plus infinity is unity. Here we established that, and gx is 0 at minus infinity. Now the third property is the right continuity, then we will establish that as well. So for the property limit, we will take g of x plus k. Okay. Now we will substitute the x by x plus k in this interval in this place. Limit x plus k, limit x plus k plus h and fu into du. So what we will do, we will take u is equal to v plus k. Okay, so du will be equal to dv, and when u is x plus k plus h, then v will be equal to x plus h, and when u is x plus k, then v will be equal to x. So what we get? We will get 1 over h limit 0 to x plus h and f of v plus k into dv. Now we are taking the limit k tends to 0. So this limit will continue here as well. Limit k tends to 0 and limit k tends to 0. Now since these limits are independent of k, so I am taking limit inside this curve f of v plus k limit k tends to 0 and dv. Now what we get? 1 over h. Since this function is also a distribution function, so this will be equal to f of v. So what we get? We got x to x plus h into f of v into d of v. So this is also equal to, this is exactly the g. So we established that this function gx is right continuous. So by the help of the integration, we have established that gx is a distribution function. Now we will take the another case where we will check to whether hx, which is defined by this function, is again a distribution function. So you can note down and we can proceed further. So we are defined as the g of h of x is defined as 1 upon 2h limit x minus s2 x plus h f of u into dv. Okay. Now what I will do, I will bring this x instead of limits to this place. Okay. So I will substitute u as v plus x. So what benefit it will yield? It will make the limits independent of x. Okay. So now what benefit I got? I removed x from the limits by substituting u plus x, u from u as v plus k. Now to establish the non-increasing, let's suppose x1 is less than equal to x2. Okay. So f of x1 will be less than equal to f of x2, and we can also add our constant v here, so we can make x1 plus v f of x2 plus v. So we brought this term here. Now I will integrate both the sides by multiplying 1 upon 2h limit minus s2 plus h f of x1 plus v into dv is less than equal to 1 upon 2h limit minus s2 plus h f of x2 plus v into dv. Okay. So what is this? This is g of x1, which is less than equal to, h of x1, and which is h of x2. So we established that hx is a non-decreasing function. Now we will check the other properties of hx. Now from this integration, I will start. This integration will be particularly important because we have made this integration independent of the limit, independent of x. So limit x tends to infinity, h of x will be given by 1 upon 2h minus s2 plus h f of v plus x into dv. So since limit, I am taking limit x tends to infinity here, so we know that this value will be 1. We see that hx, the value of hx at plus infinity is 1. Now limit x tends to minus infinity of hx, which is 1 upon 2h limit minus s2 plus h f of limit x tends to minus infinity f of v plus x into dv. Now this we know that this is 0, so and integration of 0 is 0. So we established that hx is 0 at minus infinity. Now to check the right continuity of hx, we will take limit k tends to 0 h of x plus k, which will be limit 1 upon 2h minus h2 plus h f of x plus k plus v into dv. Okay, and limit k tends to 0. Since now I'm taking the limit inside the bracket, so limit minus h to h, limit k tends to 0 f of x plus k plus v into dv. So this term, if I remove this, we substitute this will be equal to 1 upon 2h minus h2 plus h f of x plus v into dv. So this is nothing but this is again hx. So we established that limit k tends to 0 h of x plus k is equal to limit h of x. So we established that hx is right continuous. So these are the examples for today, and in the next lecture we will take some more examples from Kesa and Berger and other important books, and also we will take some inequalities from the book Gupta and Goon Gupta Das Gupta, which are of particular importance. I hope you enjoyed this lecture. Thank you very much.